Okay, welcome back. We're looking at project number 3. I'm going to check our stream settings, make sure we have audio, video, the normal AV stuff. Looks like I have an excellent connection. I'm going to check our stream settings, make sure we have. And sounds good, at least in the repeat echo for me. And so this project 3, this is our second to last project. So today, hopefully you're working on module 4, the last so one more homework, one more project. So we're getting there. We're 3/4 of the way there. Feedback on this. Most people did really well. It seemed like things really clicked after homework 3 and kind of looking at those concepts in there. I have some stuff already set up, so I'm just gonna restart everything. Let's see. So we'll run this. So the first thing I'm doing is just importing NumPy and Matplotlib. I already set up my simple rocket equation, and I saw some people kind of create their own simple rocket, and that's okay, like build a new function. The one thing that I did want to say is that if I create like a simple rocket here, so if I do this, and then down here, when I try to run if I redefine it and I start changing things, I don't know what, like change this to a positive DMDT, like, and then I run that, that's gonna overwrite any of my previous simple rocket stuff. And it also gets really confusing because now I have this simple rocket defined and I have this simple rocket defined up here. So the most likely person that has to deal with your code is yourself. Be kind to yourself. If you're going to define a function called simple rocket, define it one time and that's it. Like, leave it alone. And if you want to make changes to it, come back up to this cell and make changes. Don't have two copies of the same function that are competing with each other, because now depending on whether this is input 3 or this one is input 2, I don't know which one is running unless I run from top to bottom, and then hopefully the right one is running the way that I want it to. So that one's kind of just some advice based on troubleshooting that I've done for myself, where I have the same, usually for me, the thing that happens is I define time in 5 different places, and now I have 5 different versions of time all competing with each other depending on when I run one cell versus another cell. So learn from my mistakes, be kind to yourself. If you're gonna define a function, do it one time, leave it at that. Just, that's it. There's one simple rocket, and that's the only one that you're ever gonna touch. Okay, so that one is, so I define simple rocket. There's no gravity, there's no drag, or at least there is, but they're both 0, and I'm taking this speed of the propellant, divide by the current mass, and then multiply by that change in mass. Bigger the change in mass, the more acceleration I have, and the smaller the mass, the more acceleration I have, right? Bigger mass, smaller acceleration. So it's rocket science. And I can test this out if I'm 10 meters high, moving 10 meters per second, and I have 0.25 kilograms left. I'm gonna lose 50 grams. I'm gonna accelerate 50 meters per second squared, and I'm moving 10 meters per second. That number, this 50 shouldn't change depending on my speed. So it should be a 50 no matter how fast no matter where I am and no matter how fast I'm going. So if I'm already moving 100, I'm still going to accelerate 50 meters per second squared, because there's no velocity in that acceleration term. There's only that mass and the change in mass. And this is what this thing is supposed to do. Okay. I saw, so part of this project is, I'm going to skip ahead, then come back to where I am, is comparing solutions between Simple Rocket and Rocket, but also using one explicit and one implicit method. I saw a lot of different versions of what people kind of think is explicit and what people think is implicit. And like, it's okay to grab different integration methods, but if you're going to do, let me delete this, take my own advice, one version of Simple Rocket. If you're going to do numerical integration with these kind of initial value problems, then I'll show you the standard way of doing that. And if you're using AI to help you, try to give it just a small playground to work in. If you just tell it, like, give me an implicit method, it's going to go out there and find any random piece of code and just start generating random stuff. And it gets really messy, and it's hard to maintain if you're rebuilding these things over and over, and sometimes they work, sometimes they work for some cases. So let's take a look at the standard way of doing things. For me, I like to define time right off the bat, since it's an independent variable. I saw some people kind of creating time by appending, like say that the time step is a certain value and then appending values of time. I don't like to do that, because now that this thing that's supposed to be an independent value is changing along with all your other parameters. Most of the time it's fine, sometimes it's not. So this is, I think it's best practices based on all the training that I've had in numerical methods. And there's other ways to do it. Some people might not think that this is necessary. So anyway, I like to define my time either with linspace or array or a range, and then set my time step. That's like, this is the change in time. I'm setting up my time based on this change in mass, since I have a constant dmdt. So it's losing mass at 50 grams per second. So I know how long this thing is going to burn. I saw some people put in, this was kind of a neat thing. Like, if you wanted to look at what would happen to the rocket if it only burned for a certain amount of time and then it stopped, this was a cool way of doing it. So if m is more than or equal to 0.05, then you do this. Else so if I'm not burning anything, so if I reach that 0.05 and I'm not burning anything, I'm not accelerating anymore, and I'm not losing mass anymore. And this was, I liked this this output here. And let me make sure that these are arrays. I just like to be sure about that. And then return that D state. So I'll show you like what happens with that. Like, and so if you're going to use like other methods, like if you want to jump back into the readings and look at these explicit and implicit methods, we have ones defined in here. Those are, you can see the source code, you can grab things here. Let's go to implicit. The main implicit method, why won't it? Oh, because I went to getting to the root instead of the oscillation. There we go. So this one, you can jump in, you can grab this code, and it's an example of a simple, it's still a second order convergence. So if you have 10 times smaller time steps, you get 100x smaller error. But it has this iterative correction, and this is the main thing that makes it an implicit method. The fact that I create some kind of error tolerance, and I don't move on to the next time step until my next state, the difference between the calculated next state and the previously calculated next state reaches some error. So I'm just creating like a relative error definition and trying to get that as small as I can, get it below my tolerance. Some people use like a vector, like a linalg.norm. That's fine. Usually the sum is fine. Any kind of definition for error works. But if I want to use kind of best practice, then I would say solve IVP. This is the current like Python initial value problem solver. And let's see like how we use this thing. So I can say solve IVP. That'll give me some help on this. Default method is a Rungecutter45. So scrolling down, method. It's an order 5, so 5th order convergence. It's going to converge with, so much bigger time steps will give you much smaller error. And it has a quartic interpolation applied in a complex domain. But anyway, it's an explicit method. That one's explicit. There's also this Rungecutter23. So also a 2nd order method. Then if we keep coming down, there's other explicit Rungecutter. Here's a Redao, an implicit Rungecutter method. And then even this BDF, an implicit multi-step method. And then this LS ODA. So these are different methods that are all baked into this solve IVP problem. So let's use that RK45, just the default one. And so those are the methods that are available. And let's walk through the example. All right. And this is what I like to do. Skip down to the examples and see how to use the function. So import that solve IVP, define an exponential decay. One big difference compared to a lot of the methods that we were looking at is that it's assuming that there's time and state as 2 inputs to this function, even though I don't use the time to define the change in the state. And this one's a 1st order differential equation, similar to the heat transfer problem that we did in project 1. But I would say solve IVP of that function, this differential equation, give it the time span from 0 to 10. And then here, usually this one is just one initial value, so I might say 2. But this one is showing us like 3 different solutions, which is kind of a neat case. So if you wanted to have 3 different, you could have a list of lists for like 3 different initial conditions. If you have 2 values, here we have 3 initial conditions. And then the output is that we get this SOL, like some kind of solution where it has time, it has states, and then it'll have some other stuff too, but we can look at what that looks like. So it gives you a message. Did it work? True. It's true. It had 44 function evaluations. There were, the array is here of like what values of time it used. Part of that is because I said t eval is t, so I defined 51 values of time, and it's going to evaluate my state at those points in time. So if I change this, if I make it 501, then I get a lot more values of time. Or I can make it a lot less, right? I can just say 11. So it gives me 0 through 4 kind of half-second intervals. And then this state down here. So here's my positions, here's my velocities, and here's my mass going from 25 or 0.25 down to 0.05. And then Y events, we get none there. Success was true, still 44 function evaluations, but none. Usually all we really care about is this success parameter, this time, and then this Y. Okay, so now let's hide this Tsiolkovsky solution and just look at these 11 data points going from 0.25 all the way up to 400. And okay, it looks fine. As I'm trying to compare to oh my god. Trying to uncomment this stuff, right? As I'm trying to compare to Tsiolkovsky, this has, so it says mass final over mass initial. This final mass could be any mass, like it could be 90% of this initial mass, or it could be 50%. In our case, we're going all the way to 1/20th of it, so 0.05 or sorry, 1/5, so 0.05 over 0.25. But we can look at the whole range of masses and see how well this thing converged. So I said there were 11 data points in my simple rocket solution. So let's make the number of masses. We're going to go from 0.05 to 0.25, and I'll take the log here, and let's plot that on the same graph. So I'm saying MT and VT, and that's going to be a black line. And sure enough, it looks exactly the same as my solve IVP solution. Let's get rid of this. And what I did was grab solution y2, which is my mass, and then solution.y1, which is my velocity. I made these blue data points here. Let's get rid of that. And I can see here, oh yeah, the values are flipped. So if I look at VT here, or let's look at MT, it goes from 0.05 to 0.25. Meanwhile, my SOL.y of 2 goes from 0.25 to 0.05. So my velocity is, at least for this black line, is kind of working forward, going from 0.05 down, but my blue points are going backward. So I just need to flip the directions of one of them. So I'm going to say start at 0, go to the end, take steps of -1, and now I can see that it starts off with 0 error, and then we get a little bit of error along the way. That seems large. Oh, meter per second, yeah. So over, when we're talking about like 400. Oh yeah, we need to flip the, let's do this, sol.y bracket 2, like that. So when we look at mass, we start off with 0 with perfect agreement, because at 0 velocity, there's no change. And we could even look at a semi-log y in here. And we probably need to say absolute value of that. So we're starting off with really small error, and then we get up to 1 meter per second as we're kind of up here. And if we divide this by v sub t bracket colon colon -1 to give us a relative error, we're always at like the 10 to -3. And there's a 0 in there, so that's okay. And these pink boxes just tell you, hey, look, there's a warning in here. So 10 to -3. So the one thing about using this solve IVP, I don't have a lot of control over how this thing is integrating. Like, a lot of it is just automatically doing stuff. And that's why in the readings and the homeworks, we're using our own functions, so we could manually change these time steps and look at what is the convergence here. So even in here, as I go from 11 to 101, so 10 times more. So right now we have 10 to the -3 as our biggest error. Oh, and it would help if I do this, so we get more values of mass. We still end up with like 10 to the -3 error. We can see things changed more because we're changing how we're integrating, but for the most part, stuff is happening without us controlling it. Most of the time, it's not that big a deal. Like having point, let's change this to 100 times that. So having less than 1% error over the entire function, and most of the time less than 0.0, less than like 10 to the -4% error. It's pretty small, so we don't have to worry about it too much, but we're not controlling these time steps. There are ways we could jump in there. We could jump like a little deeper. Let's see. Y0. So we can change the method. We can change where it's evaluated. It doesn't change the time step though. Dense output, events, vectorize, args. That one's for the functions. Max step. We can change this max step because by default it says infinite. So that one might help if we want to look at like convergence. So right now, still the same kind of graph, but let's make a smaller max step, like 1/10 of that. Still the same kind of 10 to the 1, 10 to the 0. Anyway, so if you're gonna use like a new method of like grab something out on the internet, way better to use solve IVP. That's the main thing that I wanted to show, was like rather than trying to rewrite new functions, Runge-Kutta like 4 or 5 methods and all that. Solve IVP works great, and it converges. It's already gone through a lot of convergence checks, and there's teams of people that kind of work on it. Let's get rid of that one. Cool. So then we come down to Rocket, and we can use the same solve IVP process in here. And right now I'm just using that Runge-Kutta 2.3, so still an explicit method, and comparing that to that Tsiolkovsky solution. So using the same values here. And a lot of you notice that there's a change, like that this, it doesn't follow this black line anymore because we're slowing it down with gravity and drag. But we can make this a bigger term. Well, I guess we can make these seem smaller by making this a bigger term, which would mean that dmdt is our main chain. Like if I want these blue dots to line up better with this black line, I could make this 0.5, and now it gets a lot closer and I don't have nearly as much error. You don't have to do that. It's okay to just say like, okay, its velocity is increasing but not nearly the same as the simple rocket, and that's okay. Simple rocket, at least here, it seems to converge to that Tsiolkovsky, at least within 1% error. Here, we're going to have a much bigger error because we're introducing more physics. General process that we're using is called a verification step, where our numerical methods align with that Tsiolkovsky analytical solution. So we approach it from two different ways. And again, I'm scrolling back and forth. But first we say, okay, there's an accepted solution to this differential equation when these two terms are negligible. And that's what it should be. So we can plot that, figure out that yes, in fact, we can recreate that solution. So now when we start making it more physical, as long as it doesn't do something like crazy, like this velocity becomes constant immediately, then we know that we're introducing it correctly. And again, we can do that check, make this like 5. So the bigger that dmdt gets, the closer it gets to that black line, and kind of the happier we are that numerical integration is doing exactly what analytical integration would do. And so if I want to look at an implicit method, and let's put this back up at 5. So basically exploding, and then we'll grab this guy and plug it in here. And again, I should be saying like SOL, like RK2 or something. So I'm not overwriting my previous solution. So I'll call the initial solution just running from top to bottom. I don't need this anymore. Delete that. I don't need to see the whole solution. Okay, so that's my solution. Now with this Runge-Kutta 2 method, I can see I have bigger, this should be RK2 like that. And this should say RK2. And this should say RK2. Oh. As I'm relabeling, I do need to keep track of stuff that's going on, right? And why are 10 to the 4, but there's no way we're off by 1,000. So I think This does not need to flip back and forth. There we go. So now we have like 0.2% error up to 0.6% error with this method, with this Rungakutta 2. So it's working pretty well. And if I want to change that to an implicit method, I could take all this and instead of RK2, let's look at like a Radau. Because again, Radau was one of the implicit methods. Solrat. And what we should see is roughly that it's the same. It shouldn't matter whether we use implicit or explicit in these cases. Implicit will be slightly lower. And right now we're on a log scale, so these can be kind of large, but for the most part, we're always like 10 to the negative 1 error. And that's what we should expect, that there's no difference. There's nothing big happening, like no big like nonlinear events or something, or like a really stiff problem where we would expect big changes there. So first we did that verification. Now we're doing kind of the next step of like, hey, our method is convert. So we're doing a convergence study that our integration method doesn't matter. Like we can get to the right answer no matter how we approach it. Last step is that now we have this function, and that function can do whatever we tell it to. So how do we reverse engineer it? Of like, how we want to get a certain solution, like we want it to reach this certain height at a certain time. So how do we get there? And so let's look at a few different burn rates. And to start, let's just look at like 0 to 10 seconds. And we'll do 51 time steps. Rungakutta seemed like this 2-3 method seemed like it worked pretty well. And let's see how high we get. All right, so if we look at this, oh, you know what? I didn't add this part. So we want to say just want to make this an array. If m is more than or equal to 0.05, then do that. Else we want this one, so we don't want any of this, and we don't want any change in mass. And I could put a 0 right here. And this one, we don't want it. So we'll say V times NP dot absolute value of V, like that. So if it starts falling down, it's not still accelerating upwards. Anyway. Okay, so now we can start to see like some actual like rocket science. So if we're burning the whole time from 0 to 10 seconds, this thing slowly starts to increase speed. Meanwhile, in these cases, we burn real fast, and somewhere up here is where we stopped burning. That's where the explosion would happen, is like where we hit that 0.05 kilograms. But if we didn't explode, if we just like burned all that fuel and watched it launch away, kind of like a rocket launch, then this is what would happen. It would like have that initial speed, but gravity and drag would slow it down. It would kind of become like a projectile motion with drag on it. So these are kind of cool. But I don't really want to see what happens after the explosion, because really I just want to see like, okay, it explodes somewhere down here since I'm burning so fast. But it does get pretty high. It's kind of cool to see. Let's go 0 to 20. It's kind of cool to see like how high all these different things get to. So it's a different optimization problem if I wanted to look at like how high I could possibly get it. 50 seconds. Yeah, so it looks like somewhere in there, that red one, like this 0.05 instead of that 0.5, somewhere in there is the highest I could get it before it starts falling back down and reaches a terminal velocity as it's falling. Okay, anyway, I don't want it to last forever. I want it to go from mf minus m0 divided by dm, and I guess m0 minus mf, like that. So go from 0 to explosion, and if I want to see when these things would all explode, I could add a -1, a -1, and a star, and say marker size, I think it's size equals 20. So explosions here, 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 here. So somewhere between this one and that one is going to be our ideal height. So I'll define a function that returns this height minus 300. If that function is 0, then I chose the correct dm dt. That's what I want to do here. So in this case, I can grab this whole thing. Let's grab all this, since I need all those parameters, right? And do that. I don't need to define this t eval because all I really want is the last value. So then I can say my error is sol.y0 -1 minus 300. And let's look at f sub dm of 0.05. I get -242. Oh, yeah, rocket, that should work. -242. So let's come back up to 0.05 should be this one. So it gets up to like 700, so 242. So going from here, 42, 100, maybe another 100. So 242 makes sense to me. And if I make it faster, 0.5, still 242. So that can't be right? So dm dt, and here's the missing link. This value should be this dm dt, and this time should also be that same dm dt. This is called a dummy variable, because whatever I put here, it doesn't matter what I label it. It's going to use that value in the rest of this function. So even if I say dm dt equals Batman up here, where it should not work, if I say fdm of 0.5, it'll give me a solution of that 0.5. And then when I go to 0.05, I get 125. Okay, so let's go back up and double check here. Let's just look at 0.05. Let's just look at 0.05. So I get 425 and 300 is 125 away. Okay, there we go. Now we're on track. And if I change it, it goes back to that negative 240. So it seems like it's doing what I want. In this problem, I asked you to use ink search and the modified secant method. Those are nice root finding methods. There is an fsolve. So again, if you're gonna use from scipy.optimize import fsolve. So if you want to use like the current best practice method, fsolve is the way to do it. This one takes a function and an initial value, and then it does different checks and tries different ways of getting to the root of a function. And let's scroll down. Here's an example. So if we're trying to find x0 times cosine of x1 equals 4, and x1 times x0 minus x1. So here's a set of equations. We can define two different equations with two inputs and give it some initial value. Then it'll find the root for us. So the nice part about this is we don't have to worry about the Jacobian of it. It'll try to, like the derivative of that function like we were doing in the homework. So if you want a method that will work for like 90% of these kind of problems, we can do this one. So FDM 0.05 should work. Yeah, it does not work very well, right? That's interesting. What if we do that? Ooh. Okay. So it's not working very well, huh? What we might have to do is actually give it bounds in here. From ragged nest sequences. I wonder why it's having a problem. So if I try mod secant, I can give it a delta x value and an initial guess. So I want to give it something small. And here I get an answer after 4 iterations. But when I ask fsolve to do it, it should use basically a modified secant. It also uses some bracketing methods in there with the same initial guess. I get to the same value, but it's giving me some issues about this array. Ragged nest sequences. I don't know why it's complaining about that, because it's complaining about my rocket equation, but it doesn't look ragged to me unless it's trying to plug in multiple. Again, this is why you only define one function and then you edit it where it needs to be edited. So it works fine there, but it's still, again, it's giving us an output, but it's just complaining that there's an issue, there's a warning, not an error. So it does get us to the right spot. Okay, cool. That was all I had for today. So main thing, kind of wrapping up, main thing is if you want to use some more advanced code, like we're using kind of very simplified integration and root finding methods for this module. So if you want to use more advanced ones, that's great. Totally encourage you to try some new stuff. In here, I specifically asked for the modified secant, but if you want to verify that it works with a different method, use something like fsolve, like use an industry standard for solving problems rather than trying to have AI generate solutions to these problems. Just if you're going to import a solution, import the best solution. And right now, the best thing we have would be fsolve for solving problems and solve IVP for integrating problems. Okay, so that's what I had for today. Keep up the great work, and I will catch you next time. Thanks.